Our species emerged over 200,000 years ago on a small planet of the solar system, a unique planet covered with oceans and inhabited by thousands of species. This is where we evolved and bloomed, until our technical know-how and thirst for discovery freed us from Earth's gravity. Little by little, we became a multi-planet species, constantly pushing back the limits of our knowledge. Our horizon shifted from the blue planet in search of a new haven. We colonized Mars and its red deserts, swung by the moons of the gigantic planet Jupiter and its menacing eye. Then we arrived in our new world, close to Saturn, 1.5 billion kilometers from our home planet. Here, in the shadows of the giant and its system of ice rings, we found our new haven, a secret haven, protected by a thick brownish-orange atmosphere. A haven named Titan. Titan, the largest of Saturn's moons, the only moon in the solar system with an atmosphere. A moon that was an impenetrable mystery for centuries. A moon that turned out to be the best candidate in our solar system for human colonization and hosting life. A moon it took us many years to conquer, using all the ingenuity of our kind. Our adventure begins in the mid-1970s, in the secrecy of NASA's Jet Propulsion Laboratory. The Apollo missions to the Moon have come to an end, and American engineers have embarked on a new challenge: to send two space probes, Voyager 1 and 2, to explore the outer solar system and its giant planets. But Titan and its mysterious brownish-orange atmosphere so intrigue the scientists that they decide to change Voyager 1's course.
Titan has always been a source of fascination for the scientific community because at the very beginning of the 20th century, observations were made with the means available at the time, which showed a darkening around the disk of Titan. This was interpreted as a sign of the presence of an atmosphere. An atmosphere around a satellite was quite a special thing, and it spurred scientists to take a closer look.
On November the 10th, 1980, after a 3-year journey, Voyager 1 entered Saturn's system. Tens of thousands of kilometers away, Titan was close enough to be photographed. It was an historic moment. Titan's atmosphere is so thick that Voyager could not reveal the secrets of its surface. But the probe had other resources and managed to send back unprecedented data which sent the scientific world into a frenzy.
It was the discovery of a pretty remarkable world, because although the methane clouds shrouding Titan prevented us from seeing its surface directly, we were able to extract a wealth of information about its atmosphere.
Of the most important information revealed by Voyager, the presence of methane was of particular interest to scientists. Since methane, a gas composed of carbon, is one of the organic building blocks of life.
Voyager's instruments weren't optimized to study this organic chemistry. So it was natural to assume that there were other absolutely extraordinary things in the atmosphere on Titan's surface, and it was imperative to return.
A spacecraft had to be sent with all sorts of instruments, including a radar, capable of piercing through the clouds. But what they really hoped to do was send a probe, a dedicated probe, which would descend through Titan's atmosphere.
This crazy plan to deliver a probe over 1 billion kilometers from Earth to an unknown environment would be the Cassini-Huygens mission, an historic joint endeavor of NASA, ESA, the European Space Agency, and ASI, the Italian Space Agency. An impressive technological feat, the mission consisted of an orbiter spacecraft, Cassini, which would carry a probe, Huygens, and release it into Titan's atmosphere.
I would consider Cassini-Huygens as a model of how international agencies and international scientists actually work together for a common goal. And that enabled us to do significantly more than if only the United States. By bringing the best talent, both in Europe and the US, it enabled us to do a mission which will go in the book of history for many decades, to come as one of the most exciting missions that was accomplished.
November 1989. After 10 years of research and development, NASA set about building the Cassini orbiter. During its 7-year journey through the interplanetary void, the spacecraft had to be capable of performing trajectory correction and maneuvers remotely piloted from Earth. Cassini is equipped with radioisotope thermoelectric generators to power its instruments. Cameras and spectrometers are placed on one side of the craft. The Huygens probe is bolted to the other. There's a telescopic mask for measuring magnetic fields. A radar is placed on the antenna that will transmit collected data to Earth. This antenna will also serve as a shield to protect the spacecraft during critical stages of the mission. To steer itself, Cassini has a series of thrusters and 2 main engines, each capable of providing 50 kilos of thrust, a record for a space exploration craft.
A spacecraft had to be exceptionally reliable. It was built with, for example, 2 sets of all the major components, so that if one would fail, there was a backup. Building that and the autonomy to switch between them was a major development. Of course, the Titan environment was almost completely unknown, and that was a major challenge for the design of the Huygens probe.
While the Cassini spacecraft was being built in the United States, the French manufacturer Aérospatiale was given the task of developing the Huygens probe. This was the first atmospheric entry probe ever built in Europe, but also the first probe in the world to touch down on an unknown surface. For the 1980s, the Huygens probe was a technological marvel. It's equipped with 6 instruments enabling it to see, hear, touch, and even taste Titan's atmosphere and surface. The most important instruments include HASI's deployable booms for measuring the electrical properties and physical characteristics of Titan's atmosphere, an imager equipped with several sensors which would capture unprecedented images of Titan's surface, the DISR, and a series of sensors designed to determine the physical characteristics of Titan's surface at the point of impact, the SSP. To be sure this 350-kilo high-tech marvel arrived safe and sound, there would be a few more challenges to overcome.
This was the first time ever that Europe had developed a device designed to enter an extraterrestrial atmosphere, descend through it by parachute, and hopefully touch down on the surface.
We weren't very hopeful we'd be able to land it, because the engineers had told us it was impossible to land on Titan. The surface was unknown, it would crash or sink, and all sorts of other disaster scenarios.
Many studies and simulations were required to validate the shield. It had to act as a powerful brake while heating to several thousand degrees and allow the probe to enter Titan's atmosphere. The second major challenge, I think, was developing a system of 3 parachutes that had to deploy in sequence at different altitudes in Titan's atmosphere. The tests, which involved launching a mock-up of the Huygens probe with a stratospheric balloon, then releasing it in a parachute on a site in Sweden, enabled us to validate the whole parachute deployment sequence.
Spring 1997. 7 years after work on building them began, the American Cassini orbiter and the European Huygens probe were joined together at Cape Canaveral in Florida. On October the 15th, 1997, everything was ready for the launch. At 4:43 a.m., the Centaur 4 rocket lifted off from Launch Complex 40, carrying the Cassini orbiter and Huygens probe. The most ambitious journey of the space age had begun.
Standing by now to get confirmation of spacecraft
We
separation.
have confirmation of Centaur and SP separation.
That's it.
The Centaur and Titan flight performance.
Getting to Saturn is very challenging. It requires a lot of energy to get you that far out in the solar system. And the rocket that we had, at that time, did not have enough energy to push the satellite to go directly to Saturn. So what we had to do, we had to go out and then come back and fly by Venus and use the gravity of Venus, kind of give us like what we call a slingshot.
By entering the planet's gravitational fields as if it were falling towards them, then escaping their gravitational pull at the last minute, Cassini gradually increased its speed.
So by doing these multiple flyby, we were able to gain enough energy to get us actually to Saturn. And that's why it took us 7 years, to get there, is because we had to do these different flyby.
In August 1999, after looping twice around the Sun, Cassini approached Earth. Thanks to a slingshot maneuver, this was an opportunity to accelerate again and to say farewell to the blue planet. Having gained the required energy, Cassini began its long 5-year journey towards the outer solar system and mysterious Titan. A year later, in December 2000, Cassini approached Jupiter. Even though the spacecraft remained over 10 million kilometers away from the giant to minimize damage from its intense radiation fields, its cameras beamed breathtakingly beautiful images back to Earth. Late June 2004. On Earth, the tension was at its height. After a 7-year journey, Cassini was nearing Saturn. This was one of the most perilous phases of the journey. The spacecraft had to place itself in orbit around the giant planet, and to do this, it had to dive through Saturn's icy rings.
The engineers really put the pressure on by telling us it was extremely dangerous, that the probe would not survive. At least one of the instruments would break. It was complicated and so on. So we were sitting there in a state of tension. Scientific, technological, psychological.
So we were pretty nervous, when we got very close. Now, the model did tell us that it's very low likelihood, but all what you need is one particle and you destroy 15 years of work.
To pass through the rings, Cassini had to use its big dish antenna as a shield and could no longer transmit. Back on Earth, this silent passage was a white-knuckle moment. Hundreds of millions of kilometers away, no one knew if the spacecraft would survive. Despite its silence, Cassini continued to record data such as particle impacts. A poignant moment. After this initial feat, Cassini spent several hours above the rings, several magical hours. Now Cassini had to turn around and use its main engines to brake, engines that had not been used for several years. At 7:36 p.m., it fired its bipropellant engines. Once again, Cassini demonstrated its technological perfection. The maneuver was a total success.
It was quite extraordinary how the engineers managed to pass the spacecraft through the widest gap between the rings and out the other side. We breathed a huge sigh of relief. We saw the first images of the rings. We saw the structure of the particles in the rings. We saw the planet's shadow cast on the rings. We had never had so much spatial resolution on images of the rings.
Cassini was now orbiting Saturn, a milestone in the history of astronomy. The mission now entered one of its most decisive phases. On October the 26th, 2004, Cassini was about to make its first reconnaissance of Titan. It was the moment of truth for the spacecraft's instruments. To penetrate Titan's hazy atmosphere, Cassini has imaging equipment that records the infrared rays reflected by its surface. Back on Earth, the scientists waited with bated breath. Would Cassini's imager really be able to reveal Titan's surface?
When the first images arrived on the 26th of October 2004, I was still in the lab at 4 in the morning. I remember the exact time the images were supposed to arrive. And one by one, these long-awaited images arrived, and at last we could begin to discover Titan's surface. It was better than we'd expected.
Dozens of images were beamed back to Earth. Only 64 pixels across, they were low definition by today's standards, but they provided sufficient information to give scientists an idea of Titan's surface. As well as its infrared cameras, Cassini has a synthetic aperture radar for obtaining information about Titan's terrain. This radar bounces radio waves off its surface. Ground features reflect the waves back with altered wavelengths. By analyzing these changes, the onboard computers can construct high-resolution images of Titan's surface.
When we saw the first image, it didn't really make sense to us. We didn't know what we were seeing. We didn't see much familiar. There was something that maybe looked like a crater. There was some things that maybe looked like rivers, but we couldn't really be sure.
Even though they are open to interpretation, these first radar images of Titan's surface revealed a variety of landscapes whose existence the scientists had never suspected. Following these initial revelations, NASA's engineers began to focus on the mission's next phase, releasing the Huygens probe into Titan's atmosphere. A very risky phase, as Cassini first had to fire its engines to change orbit and enter a collision trajectory with Titan. The slightest error would be fatal for the orbiter as well as the probe. On December the 24th, 2004, Cassini was preparing to eject the Huygens probe. Despite the festive atmosphere, the tension was palpable. After being dormant for 7 years in the interplanetary void, no one could guarantee the probe release mechanisms would wake up. At 6 p.m., Cassini's automatic program activated the release process. Huygens began its descent, alone, towards Titan.
Detached. Released. All three. All right.
Huygens' silent descent would take almost 3 weeks. Meanwhile, to avoid crashing onto Titan, Cassini had to alter the course it had been on to release Huygens, then reposition itself to retrieve the data the probe would send it on touching down. On January the 14th, Huygens was finally nearing Titan's upper atmosphere and the moment of truth. Would the thermal shield designed to protect the probe's instruments prove effective?
For the entry into Titan's atmosphere and to break its descent, Huygens was protected by a thermal shield. The front part decelerated the probe, and the back part, the back cover, protected the instruments during this hot phase. Because the temperature of the shield itself was over 1,500 degrees. And the gas heating at the front of the probe was somewhere in the region of 8,000 to 10,000 degrees.
As the engineers wandered back on Earth, Huygens continued its journey. The thermal shield kept all of its promises and its parachutes open to break its descent. Years of tireless work had paid off. At an altitude of 150 kilometers, Huygens' instruments started up, and the probe sent its first signal to Earth. For Huygens, reaching the surface was a race against the clock, as its batteries were only designed to last a few hours.
The mission took place around midday, from 10 a.m. to 1 p.m., and we had to wait until 5 or 6 in the afternoon, local time, in Darmstadt, to get the first data via Cassini.
The mist gradually cleared. Huygens kept on snapping the landscape below it, revealing Titan's mystery as it did so.
On January 15th, we had planned a press conference, and the camera team had managed to produce a panorama, if you like, by putting 10 or 15 images together. And on seeing this panorama, when it was presented, I said, "That's unbelievable. It's the Côte d'Azur." Honestly, the panorama as it was presented reminded me of the Mediterranean, of the rivers flowing into the Mediterranean and the hills, so I saw the Côte d'Azur. That was my initial reaction. But that isn't Titan, it's the Côte d'Azur. But it was Titan.
On January the 14th, 2004, Huygens was nearing the surface. The craziest challenge in the history of space exploration was on the verge of being pulled off. A man-made craft had traveled over 1 billion kilometers to land on the surface of an unknown celestial body. All the instruments were activated. They recorded and relayed to Cassini as much data as they could before the batteries died.
Once Huygens had touched down, once it was stable, all the instruments continued to work and the camera took images of the surface of Titan.
As we had cameras in 3 directions, we had stereo images and we could clearly see around the touchdown site what appeared to be a riverbed with small round pebbles.
We were actually seeing familiar landscapes but with totally different ingredients. It is 180 degrees on the surface. So these pebbles aren't made of stone. They're ice pebbles, water ice pebbles. The sand, the matter that resembles sand, is organic matter. A mixture of grains of organic matter and grains of water ice. So, very different things from what we see on Earth, but in appearance very similar to what we know on Earth.
A few hours after touching down on the surface of Titan, Huygens' batteries died. The probe went dark. But the information it had gathered is an inexhaustible treasure trove. 13 years on, scientists are still working on it.
Huygens provides a resolution that enabled us to see details that are inaccessible to Cassini from its orbit. However, Huygens is a single date at a single spot on Titan. And to understand a complex system like Titan, you have to be able to extrapolate this data of Huygens. It's extremely precious data, the in situ truth. But you have to be able to extrapolate this data, thanks to models, by making hypotheses, at every longitude and every latitude of Titan. And this is where Cassini helps us from its orbit.
During its 13-year mission, Cassini has tirelessly explored the Saturnian system by flying by Titan every month. In all, the orbiter has made about 100 flybys. On each of these flybys, Cassini sends new information, enabling scientists gradually to map Titan. But the operation is a real headache because it means piecing together dozens of images taken at different latitudes and with varying degrees of light. If, thanks to Cassini, scientists are trying to refine their knowledge of Titan, it's because they hope to find the necessary ingredients there for the development of life.
What interests us too are the conditions for what we call habitability. Habitability is actually the measure of a world's ability to bring forth life or to sustain life once it exists. By extrapolation of what we have on Earth, the question is, what do you need? You need water, liquid water, you need nutrients, you need energy sources, because it is energy that makes our planet live, in fact, and the metabolism evolve. And you need a stable environment. For the environment to be stable, you need a pretty big world.
To check that habitability conditions exist, and to confirm their scientific models, the researchers wait impatiently for each new transmission from Cassini. In 2007, 2 years after releasing Huygens, Cassini made a major discovery. The spacecraft detected for the first time a series of seas and rivers in the North Pole region. This revelation enabled scientists to confirm the existence of an active cycle on the surface of Titan.
Titan is 1.5 billion kilometers from the Sun. It's very, very far and extremely cold. So we thought it would be a completely frozen environment with a geology and climatology that was totally inactive. And we were amazed to see that the climatology was active. Not only active, but complex. And that even at these very, very cold temperatures, there was a climatic cycle based on evaporation, condensation, the formation of clouds, of rain, and that this rain fed the expanses of stable liquid on the satellite's surface.
Methane is found in vast quantities on Titan, particularly in its lakes and rivers. When the seasons change, when the temperature rises, methane evaporates, then condenses into clouds some 30 kilometers above the ground, before falling back to the surface in the form of rain. The whole forms an active cycle analogous to Earth's water cycle. In summer 2009, Cassini captured a remarkable series of images which confirmed this, and the existence of distinct changing seasons on Titan.
The equinox occurred in August 2009. The equinox is quite simply, just as it is on Earth, when the sun shines perpendicularly, emits a maximum amount of energy at the equator. We saw the tropics, or Titan's equatorial regions, which are usually relatively calm. We saw quite extraordinary activity occur at that point. Very violent storms with torrential rain over the equator. It impacted the landscape in the same way that torrential rain does Earth's deserts, where you have dried up rivers the rest of the year, and then, at a certain time of year, there are very violent storms that fill these great deserts, which continue to erode and carry sediment toward the sand deserts, where you can see dunes forming. So Titan's dunes have a structure that's pretty amazing. They're all linear, with a very stable linearity. They can stretch in a straight line for hundreds of kilometers. In fact, We think they're quite astonishing. Not made up of sand, as they are on Earth, but of the material found on Titan's surface. They're grains of complex organic material.
The grains we can see on these dunes and this material, these brownish-orange macromolecules found pretty much everywhere on Titan's surface. There have been a number of theories, but the generally accepted theory now is an atmospheric origin. There are processes that occur far upstream, very high up in the atmosphere.
In Titan's upper atmosphere, ultraviolet radiation breaks down methane and nitrogen molecules into much smaller molecules. These then recombine to form new, more complex and much heavier compounds. As these compounds descend in the atmosphere, they combine to form the organic grains that make up the dunes, and which scientists have called tholins.
The Cassini-Huygens space mission has provided us with plenty of information about these grains, but it's not told us anything so far about their chemical composition. Everything we know about their composition for now we've learned through simulations and laboratory experiments.
These scientists have actually managed to recreate Titan's upper atmosphere in a vacuum in order to study the formation of tholins. As the UV rays providing the energy required for the experiment do not exist on Earth, they have replaced them by electrons. In the presence of these electrons, the methane and nitrogen injected into the vacuum form an orange plasma. Chain reactions occur in this plasma, leading to the production of tholins. But in this miniature environment, the quantities produced are minute, and it takes several days before the nanoparticles are visible to the naked eye. Produced in the laboratory, the strange extraterrestrial matter undergoes extensive analyses. Thanks to these laboratory experiments, scientists now have proof that Titan's surface is covered with an organic material from which life can develop. Readily convertible polymers that are essential to the formation of amino acids, the building blocks of life.
Exposing organic material to liquid water produces, in the laboratory at least, very interesting prebiotic chemicals. The amino acids that make up proteins, the bases that encode information in DNA, all the building blocks seem to be made in this environment. So there is that side, the life as we know it, if you like, water-based life.
Now all the scientists have to do is find the liquid water on Titan. But with a temperature of minus 180 degrees Celsius, only hydrocarbons flow on its surface. Finding the water would require going under its ice shell where the temperature might be higher. But to be sure, there will have to be a new mission. A mission all the more necessary as Cassini has only mapped 60% of Titan's surface. Although it is now certain that Titan has an active geology, organic materials and huge hydrocarbon reserves, giving it a unique character in our solar system, it's necessary to return to be sure that the Moon can really host life on its surface.
When we launched Cassini, we planned it for 5 years. To be in orbit around Saturn was 5 years, but we always keep margin in our propulsion and what we call the attitude control. I mean, the mechanism which we use to do attitude control. Well, we were fortunate that, it had been working for 13 years, but we're running out of propellant. So when we run out of fuel, that means we cannot control the spacecraft, anymore. But we want to make sure that that spacecraft does not hit Enceladus or Titan and possibly bring microbe with it because it was launched from Earth, so it has some contaminant in it. So we want to make sure those satellites stay completely clean for future exploration in case there is life, on them. So on purpose, we're going to target Cassini to actually hit Saturn and burn it in the atmosphere, so it will destroy everything on it. So that's a common practice we do on our spacecraft. Not that we would like to destroy them, but when they are completely done, to keep the planets kind of clean from any microbes from Earth.
On September the 15th, 2017, after thrilling the international scientific community for over 13 years, the Cassini mission comes to an end. And with it, one of the most remarkable episodes in the conquest of space. An end in the form of a sacrifice to give future exploration missions every chance of discovering life on Titan.
The next steps towards Titan exploration are going to need to be to have a dedicated Titan mission. And there's lots of options, right? We can have a Titan orbiter that can help us further map out the surface and understand where the dunes are, how they're changing with seasons, how the lakes might be changing, and further understand what the lakes are made out of and what their viscosities are like. And then also, an orbiter will help us understand Titan's interior and what its interior structure is like and help us understand that subsurface ocean. But then we also can send rovers and different types of landed assets to Titan.
Many scenarios are being studied for the next Titan exploration mission. The most ambitious involves placing an orbiter not around Saturn, as was the case with Cassini, but around Titan itself. This riskier operation would mean Titan could be observed continuously. As well as this orbiter, robotic devices would be deployed on Titan's surface. Airships adapted to the atmosphere's winds and density. And boats capable of navigating its lakes rich in hydrocarbons and organic compounds. Once Titan has been precisely mapped, scientists will be able to consider the next decisive stage of its conquest, a manned mission. But this new adventure implies overcoming huge technological obstacles.
One might be able to send kind of an advanced set of robots who might be very smart and be able to set up an initial power station of some sort, accessing water and creating some energy, and setting up some initial habitats.
Many extraterrestrial habitat projects are being studied. Among these is SHE, a module developed by several European countries and tested in a desert area in Spain.
SHE stands for Self-Deployable Habitat for Extreme Environments. The habitat is a very compact structure that is self-deployable. It therefore doesn't require any complicated assembly. In fact, the goal of SHE is to send something to the surface. And this system can be deployed automatically by robotic means, so it's ready when the astronauts arrive.
But to send these robotic modules in sufficient numbers, space agencies must first solve a very mundane problem: drastically reduce the costs of launching rockets into space, a significant obstacle to the conquest of space. An obstacle that SpaceX is gradually overcoming thanks to a new family of reusable rockets, Falcon 9. After transporting their spacecraft into orbit, they return to Earth ready for new missions. Back in May 2012, with the COTS-2 mission, SpaceX also became the first commercial company to deliver cargo to the International Space Station. Since this achievement, SpaceX has successfully carried out 11 resupply missions for NASA and retrieved the engine first stage of 13 of its rockets, 8 at sea and 5 on land.
The thing that I think that many people have not grappled with is that the radiation environment beyond Earth orbit is so severe that really any kind of long journey is impossible with our current technology. So in our thinking, we think that the biggest step that needs to happen is much faster spacecraft.
The propulsion speed of future exploration spacecrafts is undoubtedly one of the major issues to resolve in order to protect the health of astronauts. But here again, the latest technological evolutions are promising.
One of the concepts that we looked at in our book and that we think is promising but needs a lot more work is called a quantum thruster or a quantum drive or a Q drive. It's kind of like a propulsion as used by the Dawn spacecraft, which is in orbit at Ceres, that uses particles and shoots them through an array of an electric array.
Ion propulsion engines use xenon atoms bombarded with positive ions. The atoms lose their electrons and these escape at high speed, generating a reaction force that moves the probe. The thrust is much lower than with a traditional engine, but it is constant. This makes it possible in deep space to produce acceleration that accumulates and to reach considerable speeds while consuming very little fuel.
A Q drive would be similar to that, except that it wouldn't have to carry the fuel along with it, which is an advantage for launching and for mass overall to carry. It would just utilize quantum particles that pop up from space as it goes along. It seems like a really bizarre concept, but evidently it works. In tests, it has worked.
Requiring no fuel, the Q drive could accelerate continuously in order to reach dizzying speeds, shortening the journey to Titan to just 6 months.
Space agencies are already thinking about the next steps, and in particular, a concept that is currently being developed, a station that will orbit the Moon, an international moon station, if you like, where astronauts will be based. They will stay there a while and then make excursions to the surface. There would be a similar type of scenario with Mars, initially. You go into orbit because you're close to the surface. You can explore through observation first, and then make small, short manned missions to the surface. For me, this is the kind of roadmap we'll follow. The Moon, Mars, maybe an asteroid in between, and then, once that's accomplished, once there's a lasting colony on Mars, we could think of going much farther with Titan.
If we want to establish lasting colonies in space, technology is far from being our only obstacle. Our biggest problem is humans themselves. Combating psychological isolation and ensuring food sufficiency are challenges as difficult to overcome as propulsion. Challenges NASA has tackled on Earth with its high seas simulation missions.
For a whole year, the 6 of us crew members lived in an 11-meter diameter dome on a volcano. We were never in the open air because when we left the habitat to perform geological tasks around the dome, we wore simulated spacesuits. We had no real-time communication with the outside world. No telephone, no Skype, no instant messaging. We just had email with a 20-minute delay both ways. So, for an entire year, we only saw and spoke to our fellow crew members. And I was working on how we can live by producing what we need from local resources. I work with green bacteria called cyanobacteria that can be fed with elements found in the soil and the Martian atmosphere to create useful compounds. Either compounds that we can use directly, for example oxygen or biofuels, or compounds that can be used to feed other biological organisms, for example plants or other bacteria. And these biological organisms can be used to create a small ecosystem that is indirectly based on what is found on Mars, and therefore is almost independent from the Earth, and can produce virtually everything we need.
To settle on Titan, we first need to create a permanent base using local resources. Because even if we reduce travel times, our new environment will still be too far from Earth to be dependent on it. The first settlers will be scientists. Their main mission, initially, will be to ensure their survival. For this, they will have to overcome considerable challenges, the first of which will be to attain food self-sufficiency. This will involve a real understanding of the resources in their new environment. If the colony is not self-sustaining, it will not be able to welcome new arrivals and grow.
I think those initial explorers, adventurers are going to have to be very hardy people, and they're going to be making a big sacrifice. But that's been true throughout history, right? We've had colonists who've gone out into the Pacific Ocean, these Polynesians who are sailing all the way across the Pacific Ocean in tiny little boats, or Inuit, who are exploring and going for the first time into the Arctic, and inventing boats and kayaks and warm clothing and igloos and all the things they had to invent to go there, the hardship they had to overcome, and the darkness. All these things have been done before in human history. It's just that we're going to be doing it because of the time in history when we live. We're going to be going out to a farther place that's even more extreme, but we have the technology to do it.
Advances in the field of biotechnology will be crucial for the Titanians. They will enable them to improve agricultural productivity by focusing on high-energy foods requiring little space, such as insects or even algae, that will either be consumed directly or used as nutrients for other crops. There will not be huge wheat fields or barns on Titan, but high-yield microfarms. And the first colonists will have to be open to a radically different diet to what we know on Earth.
Some sort of power station or power stations could be set up where native H2O is taken and electrolysis is performed on the water to split the water into hydrogen and oxygen. Humans can then use the oxygen for breathing. Energy can be derived from chemical reactions of the hydrocarbons.
Little by little, the initial bases will grow with the arrival of new colonists. But those selected for their ability to adapt and be creative in an environment where everything remains to be done, the pioneers' life will be tough, since at over 1 billion kilometers from Earth, communications will be limited. The first settlers will have to deal with acute loneliness and isolation, and their homesickness for Earth will be all the more intense as there will be no going back.
It's not an adventure that you're going to go and come back and do a slideshow, but you're actually going to go and live there. And you can't come back because you will, in that low gravity environment, your body is going to change. You're going to lose bone mass, you're going to lose muscle mass. And if you come back, you may not even survive on the Earth in full gravity.
Titan's low gravity means the new arrivals will have to stay there, but it will be easier for them to move around. The atmospheric pressure, similar to Earth's, will do away with the need for heavy pressure suits. As protection against the minus 180-degree air, they will have heated suits like those extreme divers wear. This huge advantage will allow Titanians to be in direct contact with their environment.
So Titan would be a tremendously exciting place for humans to explore. One can imagine exploring with aeroplanes or other vehicles the Titan environment. So I think it's really fun to imagine one day what it might be like to stand on Titan's surface and see the waves at the shoreline of some of Titan's seas, or to fly over the possible cryovolcano, to maybe ski with a kite over the sand dunes. There's all these fun places to imagine exploring at a human level.
With the arrival of new settlers and the first generations born there, the Titanians will extend their territories all over the globe. Their physiology will not be the only thing to change. They will invent a culture, laws, an economic system, a history. They will go from mere survival to development. They will found a new civilization. A civilization that will blossom between Titan's surface and its upper atmosphere, where the Titanians will create incredible floating cities enjoying more sunshine. A civilization whose descendants will gradually forget the Earth where their ancestors emerged and speak with a different voice, a singular voice, which will take charge of its own destiny. Living on the edge of the solar system with significant water and energy resources, we Titanians will be a pioneering race, leading missions beyond it. And our children will be among the first to take up humankind's new challenge to reach one of the universe's many exoplanets. Titan will no longer be the distant and mysterious horizon it has been for centuries, but the departure point for new explorations.